One little thing before we move on. A side note. Remember how some limits don't exist? Well, the same is true for some derivatives. All right, let's use our definition of the derivative to find the derivative of a particular function. Let's start out with f of x equals x squared. All right, there it is. And if f of x equals x squared, well then f of x plus h is equal to x plus h, the quantity squared. So here we have it. We've plugged it into our definition. Notice x plus h, the quantity squared, is f of x plus h, and x squared replaces f of x, because that's what they're equal to. All right, then we get to do some algebra. We expand x plus h, the quantity squared, into those three terms, x squared plus 2xh plus h squared. Everything else stays the same. And we subtract x squared from the first x squared, because those add up to 0, and we're left with just those two center terms in the numerator. Now the next step is a little tricky, but hopefully you remember that you can divide both of those terms in the numerator by that h in the denominator. So 2xh over h, the h's divide out. And then in the second one, h squared over h divides out to h. So 2x plus h is now what we're finding the limit of. And remember, it's a polynomial. And for finding the limits of a polynomial, you can just plug in that limit value, h equals 0, to this polynomial of 2x plus h. And what do we get then? 2x, which is the derivative of x squared. And we're done. All right, let's apply what we've learned. We just found that if your function y is equal to x squared, then its derivative y prime is equal to 2x. Well, we could use that same method to find a bunch of different derivatives, but I did it for you, so we didn't have to spend that much time. It turns out if y equals x cubed, then y prime is 3x squared. So if you did all that work for y equals x to the fourth, you'd find that y prime is 4x cubed. Do you see the pattern yet? What if y equals x to the fifth? What do you suppose y prime is? That's right, y prime is 5x to the fourth. Good job. And in general, if y equals x to some power n, then y prime is equal to n times x raised to the n minus 1 power. Now you have a shortcut to finding derivatives. What do we call that shortcut? The power rule. Ta-da! Now let's use the power rule to find the derivative of some common functions. First, some new notation. d dx just means the derivative in terms of x. So we're going to find the derivative in terms of x of c, which is just some number, some constant, times x to the n. Well, it turns out the derivative of that is just that c constant number times the derivative of x to the n, or n times x to the n minus 1 power from the power rule. Let's see an example of that. The derivative of 8x cubed in terms of x is 8 times the derivative of x cubed, or 8 times 3x squared, or 24x squared. Neat. Here's another application. The derivative of c, some constant number, times x, well, that's just the same thing as saying the derivative of c times x to the first power. Applying the power rule, you get 1 times x to the 0 power times c. Well, that's just c. Everything else is 1. An example of that, the derivative of 3x is just 3. Nice. All right, how about the derivative of just a constant? Well, that's just like asking for the derivative of a constant times x to the 0 power, right? Because x to the 0 power is just 1. But if we apply the power rule to x to the 0 power, we get 0 times x to the negative 1, which is just 0. And multiplying 0 times c gives you 0. In other words, if you're finding the derivative of 12, well, that's just 0. Finally, the derivative of the sum of two functions, d dx of f of x plus g of x, any two functions, is just the derivative of the first function plus the derivative of the second function. And incidentally, that works for subtraction as well. It doesn't matter if you're adding or subtracting. For example, if you take the derivative of each of our functions from our examples to the left, d dx of 8x cubed plus 3x minus 12, Well, the derivative of the first one is 24x squared, plus the derivative of the second one, which is 3, plus the derivative of the third one, which is 0. So altogether, you just have 24x squared plus 3. That one comes in handy all over the darn place, and because of that, we get a name. The sum and difference rule. It's not quite as catchy as the power rule, but it's super helpful, super useful. Well, there you go. That's it. We learned the power rule, we applied the power rule, and we also got the sum and difference rule. Hopefully that improves your understanding of the material in 2.3. I know I learned a lot making a video, and I think I'm going to get better as time goes on. So I look forward to seeing you again for 2.4.